Hi, I am Sanjay Patel. Today we are going to understand the concept of ring and some definitions related to the ring concept. So this is very interesting topic. Remember that this is the fundamental of your this ring theory course of abstract algebra. So I start with the definition of ring. Let capital R be a non-empty set and suppose there are two binary operations. Called addition, which we denote it by the symbol plus. Remember, this plus need not be always the usual or ordinary addition. It's called addition and multiplication. Suppose there are two binary operations called addition and multiplications defined in R. Okay, we are going to use the symbol R for ring. Okay, so not for set of real numbers. If the set R satisfies the following axioms, if R satisfies the following axioms, then R is said to be a ring with respect to these operations, and it is denoted by the symbol R plus dot. So this structure, the set R together with the two binary operations plus and dot, is called a ring. Okay. Now let us understand what are these axioms. There are 8 axioms. All these things are similar to the group theory, so you will find interesting and simple. So first set of axioms. So I am writing the first condition: closure for addition. Okay, so closure for plus, I will write like this. For every AB belongs to R implies A plus B belongs to R. Second thing is called commutativity. Commutativity for plus. For A plus B is equal to B plus A for every AB belongs to R. So we say that the operation addition is commutative in R. Then again, third one is associativity for the operation of addition. That is, for any three elements A, B and C, we have A plus B plus C is equal to A plus B plus C, and this must hold for all A, B and C belongs to R. The fourth condition is the identity element for plus. So we can say existence of identity element, which is known as zero element. So existence of zero. Okay. There exists an element denoted by 0 in R such that a plus 0 is equal to a is equal to 0 plus a for every a belongs to R. And this 0 is called zero element. Just remember this important element. This is known as zero element of the ring. So zero element is nothing but the identity element for the operation of addition. So it is called zero element of R. The next condition is existence of negative element. Existence of negative element. For any element or for every element A belongs to R, there exists an element denoted by the symbol minus a. That element we call minus a in R such that a plus minus a equal to 0. This 0 is this element, zero element of the ring. This is equal to minus a plus a. So every element A in R has such an element which is called negative element of A or opposite element of A. This minus A is called negative element, or you can say additive inverse of the element A. Okay. And the remaining three properties are about the second operation of multiplication. 6, it is called closure property for operation of multiplication. So for every A and B belongs to the set R, we must have A into B belongs to R. So we can say that R is closed with respect to multiplication. And the seventh condition says associativity for dot. That is, for any three elements A, B, C, we have A dot B dot C is equal to A dot B dot C. This must hold for all A, B and C belongs to R. So you can group in any manner you want in this way. Okay, so these two conditions are for multiplication operation. And the last one, that is a property or axiom based on multiplication as well as addition, known as distributive laws. Okay, and these conditions say that for any two elements, there are two distributive laws. A dot B plus C is equal to A dot B plus A dot C. And second rule is B plus C dot A is equal to B dot A plus C dot A. And this must hold for all A, B and C belongs to the set R. Here, note that the dot, that is multiplication operation in this set, need not be commutative. Okay, it may or may not be commutative. That's why we have written the two distributive laws. The first one is called left distributive law, and the second one is known as right distributive law. So this is left distributive law, and this is called the right distributive law. Okay, because here multiplication is done on the left hand side of this bracket, and here it is on the right hand side of this bracket. So it is left distributive. We are multiplying on left here, and we are multiplying here on the right side. So a set R with these 8 axioms is called a ring. Okay, and this 0 element and this the negative element, just remember. And if you observe very carefully, the first 5 conditions, closure for plus, commutativity for plus, associativity for plus is true. There is a additive identity or say 0 element. Yes, this is also called additive identity. Let me write. 0 is also known as additive identity element. And the negative or additive inverse. These 5 conditions or 5 axioms says that this set R is a group, rather an abelian group or a commutative group with respect to plus. Okay, so I can define the concept of ring and an equivalent form like this. If R plus is a commutative group, and number 2, the multiplication operation is associative, and let us say closure, and let me write both the properties separately. For every AB belongs to R implies A dot B belongs to R, that is the closure for multiplication. Third is A dot B dot C is equal to A dot B dot C, and this is also true for every A, B and C belongs to R. And finally, both left and right distributive laws, left and right distributive laws holds. Distributive laws hold, then R is said to be a ring. Then R plus dot is called a ring. So this is our definition in short form or a compact form, and this describes all the properties in detail. Okay, so this is our definition of ring. You must remember all these properties, and before we take examples of different types of rings, let us define some more important concepts related to this. You must have noticed that we have not mentioned commutative property and unit identity element for the operation of multiplication. So if you keep on adding some more conditions for the second operation of multiplication, then we'll get different types of rings. So our next definition is the definition of commutative ring. Again, a very important type of ring, commutative ring. A ring R with respect to plus and dot, these two binary operation, is said to be a commutative ring is said to be a commutative ring if A into B is equal to B into A is true for every AB belongs to R. That is, multiplication operation is commutative. That is, multiplication operation is commutative binary operation. Okay, then it is said to be a commutative ring. Very, very important type of ring, remember, called commutative ring. So that is one thing. Another important thing about the second operation is we can define the identity element for the operation of multiplication, and that identity element is given a special name and it is known as unity element. It is known as unity element. Okay. So let us define this. Let R plus dot be a ring. It is in the ring. If there exists, remember there may or may not exist in the ring. If there exists an element denoted by, which we shall denote by the symbol 1. Remember, this is not our real number 1. In R, such that A dot 1 is equal to A is equal to 1 dot A for every A belongs to R. Please note that multiplication operation need not be commutative here. So we have to check both the things. A into 1 is equal to A and 1 into A is equal to A for every A belongs to R. So if there is an element in the ring denoted by 1 which satisfies this condition, then 1 is called the unity element of the ring R. Said to be unity element of the ring R. Remember, it is always unique, can be proved very easily. Okay, so this is another important thing about ring definitions. The next thing I want to consider is the definition of an element in a ring which has inverse, multiplicative inverse. So next thing is known as unit. Okay, remember unit and unity both are different things. That's why I'm taking here both the things simultaneously. Let R plus dot be a ring with unity. Now this is important here, with unity element 1. Okay, so R is a ring, need not be commutative, but it has the unity element. Note this. And let A belongs to R be given. Okay, A is any element of the ring R. If there exists some element B belongs to R such that A into B is equal to 1 is equal to B into A, then the element A is called, this A is called a unit, is called a unit of the ring R, of the ring R. So this number A is known as unit of the ring R, and in this case B is called the inverse of A. So let us write a remark. In this case, here in this definition, in the above definition, B is called multiplicative inverse. Is called multiplicative inverse of A. Okay, it's called multiplicative inverse of A and denoted by A inverse. Okay, remember that if A is a unit, then by definition it is clear that the multiplicative inverse B is also a unit. So let me write, if A is a unit, then so is its inverse. Okay, if A is a unit, then its multiplicative inverse, that is B, that is same as B, is also a unit. Okay, so we define ring, commutative ring, and unity element. Another very important definition related to ring is the definition of, say, something called zero divisors. We will understand all these things by different examples of rings. So definition of zero divisor. This is also a very important definition. Let R plus dot be a ring. Need not be commutative, need not having the unity element. And let A belongs to R and A is non-zero element. A is a non-zero element. Remember, we are given a non-zero element. If there exists some element, at least one element, say B belongs to R with B not equal to 0, such that A into B is equal to 0, A into B is equal to 0 is equal to B into A, then this A is called a zero divisor. Is called a zero divisor of the ring R. Zero divisor of the ring R. Understand, it is very important definition, zero divisor of the ring R. So given a non-zero element, if you can find another non-zero element whose product with the given element is 0, so that means we have this condition. From this definition it follows that if A is not equal to 0 and B is not equal to 0, implies A into B equals to 0, then this A is called zero divisor of the ring. And if A is a zero divisor, at the same time I can say B is also a zero divisor of the ring R. Okay. This also we can write in an equivalent form by taking negation. Okay. Let me write this. So then A as well as B are zero divisors. They are called zero divisors. This condition I can write in an equivalent form as if A into B, taking the negation, is not 0, is not equal to 0, implies A equal to 0 or B equal to 0. Okay, so we have A and B not equal to 0, but either A is 0 or B is 0. Okay. Fine. To understand this concept, we'll take Let us take one example at this moment so that there is no confusion as this is a new thing for you. To understand this, let me take the set which we have defined in our last lecture, set of residue classes. So let me take one set, say Z6. Z6, contains 0, class 1, 2, 3, 4 and 5. It has 6 elements, 6 equivalence classes or 6 residue classes modulo 6. Okay. And I am taking the operation of multiplication modulo here. Let us take dot is equal to dot 6, that is multiplication modulo 6. This dot 6 also some people write using this notation, cross 6. Okay, multiplication sign. So here if I take A is equal to one non-zero element, say 2 belongs to this set Z6, then it is clear that this element A is non-zero because 0 element is this. So class 2 is not same as class 0. Okay. And for this element we have to think, can we find something like B so that A dot something is equal to the 0 element. Okay. That is what I want is A means 2, dot means dot 6, say let us say dash is equal to 0. 0 means the class 0 here. So can you find some element here so that class 2 into some class is equal to class 0 from this set? Let us put one by one. If I put say 1 here, okay, this must be a non-zero element. Can you find a non-zero element in this place, in this blank space? Because according to our definition, what we have written here is, given a non-zero element, if you can find another non-zero element such that A be equal to 0. So here class 2 dot something, put the second element 1 here. So 2 into 1 dot 1 is equal to 2, which is not 0. So this is not fine. Let us put 2 into 2, that is 2 to the 4, and 4 modulo 6 is 4. It is also not equal to 0. But if I take now another element, say 3, the next element 3 here, non-zero element, then 2 3 is 6 and 6 is same as 0 because the remainder when 6 divided by 6 is 0. So here we get that condition true. So for this element which is not equal to 0, this 3 is not equal to 0. Okay, but so we have this element class 2 is a 0 divisor, and as well as 3 is also 0 divisor. So both are 0 divisors. In simple language, what you have to do is find out an element A, non-zero element, which you multiply with some other non-zero element, gives the result as 0 element. Does it have any other 0 divisor? See, we have seen that 2 and 3 are 0 divisors. But can you find some more 0 divisors here? Suppose if I take 4, then can we have 4 dot something is equal to class 0? So let us put one by one. 4 1 2, 4 ones are 4, 4 twos are 8. 8 means 6. Sorry. What I have done here? Yes, that is a mistake. I must write 5. It is 0 to 5, not 0, 1, 2, 3, 4 and 6. It is 0 to 5. This was a mistake. Yes, 0, 1, 2, 3, 4, 5. Now, if we put 1 by 1 non-zero element here, can we get 0? Say 4 into 1 is 4, which is not 0. 4 into 2 is 8, and 8 is same as what you have to do when you write when you write 2 here, the product of these two is 4 into 2 is 8, but we should not write it. We should write the remainder when 8 is divided by 6. So it is what? 2. Okay, so remainder when 8 is divided by 6 is 2. And 2 is also not 0. So 4 into 2 is 2. It is not 0. If you put 3, then yes, you will get 4 into 3 is equal to 0. Why? Because if you write 3 here, 4 3s are 12, and 12 is same as 0 because the remainder when 12 divided by 6 is 0. So one should write directly also instead of writing 12. Just simply write the remainder when the result of this product is divided by 6. So 4 and 3 are also 0 divisors. Okay, 4 and 3 are also 0 divisors. What about 5? Let us check for 5. If I consider 5 and write 1 by 1 all the elements here, can I get 0? This is my question. So what should I write over here so that 5 into something is equal to 0 with respect to the operation of multiplication modulo 6. So put 5 into 1, 5, not 0. 5 into 2, 10. But 10 means 10 divided by 6, remainder is 4. And 5 into 3, 15. 15 modulo 6, that is 3. Because 6 is 12 and remainder is 3. Then 5 4s are 20 by putting 4 here, equivalence class of 4. So 5 into 4. This is equal to, just a minute. So 5 dot 4, that is 5 4s are 20, and 20 divided by 6, okay, is equal to 2 because 6 3s are 18 and the remainder is 2. So that is also not equal to 0. So I cannot keep 4 also. Can I keep 5? 5 into 5. 5 into 5 is 25. And 25 is congruent to what modulo 4? It is congruent to 1 modulo 4. Because 6 4s are 24 and the remainder will be 1 when 25 is divided by 6. So there is no element in Z6. There does not exist any element, say class B, belong to Z6 such that class 5 dot 6 class B is equal to class 0. So there is no non-zero element. I should write not 0. Okay. So that means this class 5 is not a 0 divisor. Is not a 0 divisor. So now do you understand? So what are the 0 divisors of this set? So 0 divisors are in the set Z6 are 2, class 3 and class 4 only. These are the only 3 elements which are 0 divisors. While class 1 and class 5 are not. They are not 0 divisors. They are not 0 divisors. Okay. So can you observe very carefully about the elements of Z6 and the 0 divisors? Which numbers are 0 divisors here? these are the elements 2, 3, 4 which are not zero divisors, and 2, 3, 4 are zero divisors, and 1 and 5 are not zero divisors. So when an element is not a zero divisor, that is very, very important for us. Can you observe? Yes. See, these 2, 3 and 4 have something in common with this element, with this number 6. Okay. So what is that? All 2, 3, 4 has a factor common with this. So the GCD is not 1. While GCD, that is the greatest common divisor of say 6 and 1, is 1, and GCD of 6 and 5 is also 1. In short, 5 and 6 are relatively prime, and 1 and 6 are also relatively prime. So this suggests that in the ring in this set Z6, an element is not a zero divisor if it is relatively prime to 6. And not only for Z6, you can generalize this result for any value of n. Okay. So let me just state very important result as the conclusion of this lecture as a homework. Prove that an element class A belongs to Zn is not a zero divisor, is not a zero divisor. Okay, if and only if GCD of A and N is equal to 1. Okay, this result is very easy to prove using your number theory concepts. So I leave it to you as a homework. It will be an interesting exercise for you. So in this lecture, we have defined ring and some special type of ring, a commutative ring, ring with unity, and say the concept of zero divisors. In the next lecture, we'll be taking some various examples of ring, and we'll check all these conditions. Thank you.